For a guitar pickup to work properly, a single strand of wire, the thickness of a human hair, has to be wrapped around a bobbin thousands upon thousands of times. All it takes is one little glitch in this single strand of wire to make a pickup defective. In this video, I'll show you how to diagnose a damaged pickup and demonstrate some solutions for repairing them, besides doing a full rewind. As a quick initial test, you can use a patch cable or a simple homemade tester plugged into the guitar jack. Set your multimeter to 20k ohms or 200k if you're using an extremely overwound pickup that reads out over 20k. Attach your alligator clips to your multimeter probes or touch the probes to the tip and sleeve of the cable. Make sure your volume and tone knobs are all turned to 10. And watch the multimeter as you move the switch to select different pickups and pickup combinations. You'll notice zero resistance when I move to the middle pickup, which was the weak and thin sounding pickup you heard when I was playing this guitar earlier. You may be thinking, aha, we found the culprit. But as you can see here, by flicking this series parallel switch, the middle pickup suddenly has a perfectly normal readout. This demonstrates the need to test the pickup independently from the guitar circuit. With the pickguard flipped, we can see that testing the output of the circuit gives us zero resistance, and testing the solder joints on the back of the pickup gives us the expected readout. This pickup looks good to go, but to verify that further, we can plug the homemade tester into an amplifier, remove the pickup leads from the guitar circuit, and attach the alligator clips to them. This will allow you to tap test the pickup outside of the guitar circuit. And it's perfect for testing pickups when there's no guitar at all. However, this test does have its limitations. For example, this pickup would appear to pass the tap test. But when we hear it in the guitar, something is very obviously wrong. What's wrong is a defect I deliberately induced in this pickup. I wound the coil normally, but when I broke the wire, I wrapped it around the coil a few times instead of tying it to the eyelet, and continued to add another couple hundred turns. I then tied the finish wire to the eyelet. If this connection breaks, the hookup wire soldered to the eyelet will not be electrically connected to the coil at all, and your pickup will simply have no output. But with a break elsewhere in the coil, it creates an open circuit. The pickup still has some output due to capacitive coupling. Also known as AC coupling, this is a phenomenon where alternating current is able to pass through a circuit without the DC signal by means of a capacitor. In the case of guitar pickups, which are essentially inductors, it's more specifically parasitic capacitive coupling. The many layers of magnet wire are directly on top of each other, which capacitively couples them together. This may also be referred to as self-capacitance or internal capacitance. In other words, with an internal wire break on a pickup, the DC signal is blocked, but the AC signal is able to cross from one part of the coil to the other using the parasitic capacitance as a bridge. It's interesting to see that the wire is completely severed in this coil, but it still gets a capacitance reading of 72 picofarads, compared to 107 picofarads in the other pickup with the same turn count without an internal wire break. As for diagnosing an internal wire break in a pickup, that is, an open circuit, you'll find very high resistance, typically in the megaohms range, as you can see here, and when plugged in, significantly lowered volume with no low-end frequencies to speak of. As a heads up, you may need a good meter to see this. For whatever reason, my cheap multimeter comes up with zero resistance at the solder joints and only gets a reading when tested at the pickup leads, both in the 20 and 200 megaohm settings. With that out of the way, let's take a look at another enigma. Everything seems to be fine, but the notch positions are out of phase. You can tell because the middle pickup sounds perfectly fine by itself, but when in parallel with the bridge or neck pickups, it has a drop in volume and a thin, nasally tone. Very easy fix. You simply desolder the leads and resolder them in opposite locations. So if the black wire from your pickup was going to ground and the white was going to hot, swap them so the black wire is going to hot and the white wire is going to ground. Now everything seems fine, but upon further examination, the pickup is doing something strange. Weird. I don't remember wiring a kill switch into this circuit. However, I do remember building another defective pickup on purpose. I stripped the insulation off the magnet wire so it would form an electrical connection with the Polepieces. This simulates wire insulation breakdown on Fender pickups where the wire is wrapped directly around the rod magnets. DC resistance will appear normal, but the continuity setting has a different story to tell. Touch one probe to the start lead and touch the Polepieces with the other probe. It'll beep if the magnet wire insulation is stripped and forming an electrical connection with the Polepieces. Notice if you put a probe on the finish lead and test for continuity with the Polepieces, you'll get nothing. Performing the tap test, you can hear more hum when the leads are reversed, but otherwise no difference. But when the leads are reversed, you get a loud buzz if you touch your fingers to the Polepieces. This doesn't happen when the start lead wire is going to ground. Now for some solutions without doing a complete rewind. In the case of a wire break, whether it's right at the finish lead or buried somewhere in the coil, the process is straightforward. First, you have to remove the finish lead hookup wire. The Stumac nut and saddle vise works great to hold the pickup in place as you work. Heat up the solder joint and pull the wire out. Use a solder sucker so you have a clean hole to tie the wire around later. Cut or pull off the finish wire at the eyelet so you can begin unwrapping it. Unwrap the wire until you find the break. If your finish wire was simply disconnected from the eyelet, you only need to unwrap it enough to tie it and solder it back on. If the pickup is wax potted, you may need to heat it up with a hairdryer to melt the wax. Otherwise, it might hold the wire so securely that the wire will break if you try to unwind it. Once you've found the break the wire off a few inches from the eyelet. Straighten the wire and grab a small section of it, then tie it. Thread the wire down into the hole from the top of the flatwork and pull it. Repeat this process several times. Then simply hold the wire close to the flatwork edge and pull it until it breaks. Flip the pickup over and load the eyelet with solder. Straighten the finish lead and hold it up to one side of the eyelet while you heat the other side. It'll push right in. Thread the finish lead through the hole and you're done. This particular pickup now reads out at a solid 5.9k ohms. If you want to preserve the original wire and turn count, you can wrap the wire from the pickup around an empty spool until you find the break. To splice the original wire back on, unwrap some wire from the pickup and tape it down. Tilt the pickup back to elevate the wire and pull it taut. Apply some flux and tin the tip of your soldering iron. Grab a small length of wire from the spool and line it up parallel over the pickup wire. Run the tinned iron over both of them to splice them together. Clip off the excess wire and verify the integrity of the splice with your multimeter. One probe on the start lead and one probe on the splice. Then wrap the rest of the wire back onto the pickup bobbin by hand and tie it and solder it as demonstrated earlier. Note that if you're using plain enamel or formvar coated wire, you'll need to mechanically strip the insulation, as a soldering iron will not melt the insulation off. Use clear tape to hold the wire down and tilt the pickup back to pull the wire taut. This will make it very easy to carefully scrape the insulation off with an X-Acto blade. For wire coming off a spool, you can use the same technique. Once the insulation is stripped off, it'll be ready to tie and solder. Sometimes you can get lucky and get a pickup to work again by simply reflowing the solder joints with a little flux and a tinned iron. It only takes a minute and is worth trying before diving into a more involved repair. As for the pickup shorting to the pole pieces, because the problem is so deep in the coil, the only real solution is a complete rewind. However, all the issues here only happen when the leads are reversed, finish wire going to ground and start wire going to hot. The only reason to swap the wires is if your notch positions are out of phase, as demonstrated earlier, and fortunately, you can change the phase by flipping the magnetic polarity instead of the wires. To test the polarity, I use the Shatton magnetic polarity tester. White means north and black means south. You can see this pickup is south up. To remagnetize the pickup in the opposite polarity, I use the Mojotone benchtop magnetizer. Mounting it on a 1.5-inch block allows you to turn the handle without hitting the bench and makes it much easier to use. Open the jaws wide enough to accommodate the pickup, then tighten it until it touches both ends of the pole pieces. Back off slightly so you can pass the pickup back and forth a couple times to make sure you hit every pole equally. Then pull it out. The polarity is now north up, the same as the other pickups, and we can wire it back up with the start wire going to ground. It won't be hum canceling in the notch positions anymore, but it will be in phase. One more note on magnetizing. It's worth getting a Gauss meter, such as the WT-10A, to test the strength of the magnets. You simply hold the probe with the marked side up and put it flat against the magnet. It'll tell you both the polarity of the magnet and the magnetic strength in milliteslas. Milliteslas are 1/10 of 1 Gauss, so for example, a reading of 100 milliteslas would equal 1000 Gauss. In my tests, 950 to 1200 Gauss is average for an Alnico 5 rod magnet. But you don't need to know the Gauss of a given magnet type if you're simply looking to diagnose a weakened magnet. If one pole piece reads out drastically lower than the others, you've found your culprit. Then it's back to the Mojotone benchtop magnetizer to solve that problem, assuming the magnet has not been damaged and can still hold a charge. Hopefully this video helped better your understanding of single coil pickups and their potential problems and solutions. I know it can seem a little intimidating, but at the end of the day, they're very simple electromagnetic devices, and there's only a small handful of things that can go wrong. Thank you so much for watching, and I'll see you again in the next video.